networking, security, and Wireshark.
So I had intended to spend this video talking about very, very low level TCP issues in Docker that I've been working on. But my brain is scrambled. I'm way too tired for that. So I thought, let's just do shell shockers. So I'm going to use this really fun online multiplayer game, Shell Shockers, or shellshock.io, to teach you a little bit about TCP. So we're going to play the game a little bit. I'm going to show you what the capture looks like. We're going to talk about TCP and how it works. And then hopefully this is fun and entertaining and a little bit educational for you. Before we get started, a couple of things. Number one, I've got Wireshark open. I'm going to do a wide open capture on my Ethernet interface. So I'm not putting a filter or capture filter. I just want to capture everything. I don't know yet what IP addresses are used to communicate with shell shockers, because there's obviously the actual domain, but the actual game traffic to the server is what I want to capture. That may or may not be to the same IP. So I'm going to capture everything and filter it later. So double click and that's going to get started. Now the next thing is I want to, in browser, I'm using Edge. You know, you can use any of the browsers, they have the same feature. F12 to open the debugging tools. What I want to do is actually, in the debugging tools, I want to go to the network, and I want to preserve log. This is going to capture all the requests to the network for various resources as I play the game. Now, there's not showing any right now because I've already loaded the page. But if, for example, if I reloaded the page, you're going to see a whole bunch, right? I want to capture, again, specifically the connection between my browser and the actual game server, being the one that actually is hosting the game. So without further ado, I'm going to actually just clear this out because I don't want that data. I'm going to move it over and let's play shell shockers for a few minutes. Thanks. I play this game all the time with my son. It's super fun if you haven't played it before. But let's play a couple rounds and then we'll look at it in Wireshark. All right, here we go. I'm on red team. All right. Let's go. Oh, missed him. Ah, he shot up and I shot down. Okay. All right, let's try this again. Okay, let's go for blue. Come on. Oh no, blue won that one. All right, let's go find some blues. I'm gonna go down here. I'm gonna throw a grenade. All right, let's go for it. Come on, blue. These guys like to cancel. They're snipers. Let's jump on this guy. Come on, Mr. Egg. Come on. Let's do this. Come on. Get him. Got him in the air. Let's go to the next one. All right. Another one. 2 down. Third coming up. Third down. All right, let's try to capture this. Come on. Take over. Oh, no. Take her. Come on. Here we go. Jump. Oh, I almost got him in here. Just trying to do the same thing. I'm gonna go get him from behind. Oh, I'm dead. Okay, let's take a break. Let's look at this on Wireshark. All right, so what I've done, first of all, I've muted the actual game. And second of all, I stopped my Wireshark capture. So this is just the data I captured until just now. Now, I want to reopen the developer tools. What I'm trying to do is find what domain, so really what host name and what IP, is responsible for the actual game traffic. And when game traffic, I mean the traffic when I actually load the game, right? There's got to be a server running the game where when I do my commands and actions, it goes to that server. And then that server responds back with what's going on in the server, right? What all the other players are doing. That's what I want to identify. So there's a couple of ways of doing that. I want to first of all look in here for WebSockets. Now, a WebSocket looks like this. You see this little icon back and forth. A WebSocket is a type of TCP connection that is used in web applications, and specifically for applications that require almost near real-time communication back and forth between client and server. So a video game that you're playing a multiplayer or playing multiplayer with other players is a great example of something that would use a WebSocket. Now I can see there's different WebSockets here. I can see there's, let me just open this up more so I can see. There is a WebSocket connection to shellshock.io to the services path. And there is another WebSocket connection here to what looks like a CDN, EGS, static live, US East, a bunch of characters, .shellshock.io. Okay. So if I was a betting person, I would assume that the actual game traffic is going to this game path, to this CDN. And so what I can do is actually, I'm just going to try to copy this out. Let's try to make this a little bit bigger. Okay, I'm going to copy that. I'm going to take that into my command prompt, and I'm just going to do a really quick NS lookup. And there we go, 45.32.5.217. So that is the IP address that I'm assuming the traffic is going to go to, but let's go to Wireshark and actually validate that. Now, when you're in Wireshark, one of the easiest ways to be able to pick out streams from within a large capture that's wide open is to do it using the conversation view. So what I'm going to do is I'm going to click on Statistics, Conversations. And now I'm going to look at the IPv4 tab to start. Now, I'm going to make an assumption here that the traffic to and from my machine to the destination is going to be high relative to other traffic on the machine. I'm not really doing anything else on this machine right now, except for playing shell shockers, right? I think I have a webcam running, but other than that, that's about it. So what I'm going to do is actually sort this by the number of packets. And this just, it's a one way of identifying or trying to identify high volume conversations, because likely those are going to be the conversations that are actually driving, that are part of the conversation you're looking for, if it's something like a game where there's a lot of traffic. Okay, so in this case, remember this IP that I just mentioned, 45.32.5, 45.32.5.217. So I'm seeing here that this conversation is happening. It's got a lot of data, or relative to others, it's a lot of data, right? The top one is this. This is a webcam, I know that. But it's a ton of packets. And with online games, you don't necessarily have like the biggest size packets, if that makes sense. Because really what you're trying to exchange is like little pieces of information, talk about like position and actions and things like that. But I'm suspecting that this is the actual one that's holding my game traffic. Now, another trick you can do in Wireshark, if you want to try to, again, be sleuthy and identify different what IP addresses correlate to certain applications, is you could go back to here, you can go to View, Name Resolution, Resolve Network Addresses. What this does is it takes any IP address it finds and it tries to resolve it to a DNS name. And so when we go back to the statistics window, what we can do now is actually turn this on. And you can see here, oh, put it back on. That domain name is actually the one that, oh, go back on, please. That's the domain name that I actually saw within the browser. The other piece of this is that the second one that I was kind of thinking maybe this might be it. This is GOG. If you've ever had the good old games client for like old school games, that's what that is. So I know that's not it. So I'm going to make an educated guess that this is the stream. So I'm going to turn this off. I'm going to right click on this line, apply as a filter, selected A to B. And when I go back to my window, I have this nice big TCP stream. I know this is one TCP stream because we have one TCP handshake, which we're going to get to, and a bunch of data. Before we actually get into TCP, let me just turn off name resolution because it kind of hurts my eyes. So now we have IPs. And now we're ready to do our analysis. So before we do that, I'm going to do a little bit of theory, and I'm going to come back to Wireshark. All right, so let's cover some theory. TCP basics. Now, TCP is one of the two main, what are known as transport protocols in networking. Okay, for those of you networking heads, this is a layer 4 protocol. And there are two major protocols here. There's TCP and there's UDP. You'll probably have heard about UDP as well. So TCP is a protocol that allows you to transport data between a client and a server, right? Client server, reliably, meaning that every packet I send from my client to the server has to be acknowledged by the server. The server has to get it and send me a receipt back that says, I've got that packet, before you can actually continue going with a lot of data, with the next set of data. And vice versa. If the server sends me a packet, I need to acknowledge that before I can actually move on. If something gets lost, so like a packet gets lost in transit between the source and destination, it will be retransmitted. So if I send this one packet and somehow it gets blocked before it gets to the server, I'm going to send it again in a retransmission. And that effectively is how it ensures reliable transport, but it also slows things down, because you can imagine if you're sending 1,000 packets to the server and say you lose one, well, and the one is in the middle of the stream, well, you may have to actually stop and go back and pause and send that packet again and make sure the server gets it before you can actually keep going. So there's some inefficiencies with TCP because of that. But the upside is that you have reliable transport. Everything you send has to be received and vice versa. Now, the other protocol is UDP, which is unreliable transport. And unreliable just means that if I send a packet, I send a packet, right? It's best effort to get to the other side. There's no mechanism to track this packet or this packet or this packet to see if it was received. And the server, the same thing, right? The server will send you packets. Now, UDP is good because there is no overhead in terms of retransmission, in terms of retransmission mechanism. If I lose this packet, well, these packets are still going to go on their merry way. They're not going to stop and have like a funeral for this packet. They're just going to keep going. But that means that you have a hole in the data. You're not going to have full, reliable transport of the data. You're going to have missing things. Now, you may think that's a huge downside, but there's different applications that are better with UDP and different applications that are better with TCP. Something like voice or video, real-time streaming is actually much better with UDP. Because if you're having a voice conversation with someone, and say like there's like an issue with like the phone line, right? Like you get some of the voice traffic gets dropped. Well, you don't want that to hear the audio replay itself again from a few seconds before. You want to keep your conversation going. So what you'd rather hear is just silence, and then the conversation keeps going from when the packets catch up. So that's why with real-time like communications, UDP is better. UDP is also used in a lot of game protocols for a similar reason, right? It's a less overhead protocol than TCP. However, now in this game, it's a web-based game, meaning it's played through the browser, and a lot of those games are built on TCP, and that's fine. It just means that there's a trade-off between the reliability of the data transfer and the performance. But if you do this kind of capture on other games, you may see that they're actually using UDP and not TCP. So with TCP, first thing you always learn about TCP is that there's a three-way handshake in TCP. The client that wants to connect to a server, so in this case it's the Wireshark server, sends what's known as a SYN packet to that server. Okay? SYN stands for synchronize, and I'll explain why when we actually look at the numbers. The server then receives that and sends a packet back that's known as a SYN ACK. Okay. Now this is basically to say, hey, yeah, I got your SYN, your synchronize. I'm going to send my SYN to synchronize to say, basically acknowledge that I'm going to allow you to open this connection. And then finally, this client sends over a final acknowledgement packet, ACK, to tell the server, okay, ready to go. And then everything subsequent to that in terms of data transfer, all the packets downstream, are going to be application layer data. So actual data being exchanged between the applications. So let's actually take a step back. Let's actually go into Wireshark and show you what the three-way handshake looks like. Now I'm back in Wireshark with the same filter I had applied before. And Wireshark will actually highlight in the description, in the info field, what the flag, the TCP flag that packet has. In this case, you'll see it says SYN, and then SYN ACK, as we described, and then ACK. That's the first three packets of this conversation. Now, I mentioned that SYN is short for synchronize. Now, what are the client and server synchronizing? Well, they're synchronizing something known as a sequence number. Okay, so let's actually open this up a little bit. Let's click on the first packet. Let's open up TCP dissection. Dissection is really, think about this as going into the bytes, the bits and bytes of the actual packet and breaking it down in human readable format so that you can actually read. This is one packet. I'm reading through the packet from start to finish, but it's breaking it down in a tabular format that's easy for me to see. So, SYN, what you're going to see here is that the sequence number is 203.7345819. This is a number that is selected by the client as think of this as like a reference point. Okay. This is a number that I'm going to use to help me track the data that's in flight between the client and the server to keep track of where you are in the sequence. Because remember, TCP is reliable. So if I have packets going, I need some way of knowing this is packet 1, packet 2, packet 3. Okay. So when I lose a packet, I have a way of tracking it relative to the other packets. And that's what the sequence number is. Okay. So the client has a sequence number as a starting point. This is the starting sequence number. If I actually go to the next packet, you can see the SYN-ACK. The server, remember, because 45 is the server, it's shell shock, has its sequence number as well. This is the server sequence number to keep track of data going from the server to the client. Because remember, in this conversation, you have two different, or in this connection, you have two different directions of data transfer. Okay, you have, and let's keep it relevant to the actual video game here. In this game, I make that connection, right? We have the TCP three-way. And then every time I make an action on my machine, I have to send that data to the server. These are my actions. Okay, I click a button, I shoot a gun, I throw a grenade. I have to inform the server that I'm clicking the button and doing that. So I have to have data transfer going to the server. The same thing is that all the other players are interacting with the server, and there's a current state of the world that I'm playing in that I need to have an update, a reference of, because I'm navigating that world. If someone's shooting me or someone throws a grenade at me, I need to know about that. So the server has to be sending me that data back. Okay, and these are the actions from the server. So there's two directions of data transfer, and those sequence numbers are each side picks a number to start at, an arbitrary number. Say this is X and this is Y. And as the data is being sent, you increment that value. So it's X plus and Y plus. X plus, some number, and Y plus some number. I'll show you what that looks like in a sec. But that's really why it's called SYN, or synchronize, and that's why each side will synchronize with the other one. This is the client synchronizing with the server, telling it what its sequence number is. And then the server synchronizes with the client, telling client what its sequence number is, so they can both keep track of where they are in terms of overall data transfer. Now, the other piece of this is that how do these packets actually get, marked as a SYN or SYN-ACK or ACK? Well, TCP works on a flag system, or it employs a flag system where in the TCP packet itself, it's also known as a segment. A TCP, the piece of the packet that is TCP, right, is known as a segment. There are things known as flags. Okay, if I actually scroll down here, you can see here I have flags. And the flag is basically a bit. And if you set the bit, you set it to 1 as opposed to 0, that indicates something. So in this case, if you set this bit to 1, it is a SYN packet. Okay. This one, coming back from the server, it's a SYN-ACK. So it has both the SYN flag set and then the ACK flag set, or the SYN bit set and the ACK bit set. And if you can see here, I can see that I've got the SYN bit set and I've got the ACK bit set. And that's how I can interpret this as a SYN-ACK packet. And the final one is just ACK. And lo and behold, I just see ACK set. So that's how the handshake works. That's how I pick out SYN, SYN-ACK, ACK. That's how the actual packets are constructed to flag each other like this is the type of packet. And then you have why, again, it's called a SYN and a SYN-ACK is because you have a sequence number that needs to be synchronized. So that's the first bit, is the handshake. Now let's actually get into how data is transferred and how these sequence numbers actually matter to that transfer. So let's do some sequence acknowledgement analysis. Now, before I get into that, I want to note that in this, I actually have two different TCP conversations. right? This filter is just on IP addresses. So myself and the remote Shellshock web server. However, between these two IP addresses, we can have multiple different conversations going on. Think about it like you're calling your buddy on your phone, your cell phone, but you're also calling them on your landline, and you're also texting them. Okay, you're between yourself and your friend. Your address, your identities are the same, the IPs are the same, but you have multiple different conversations running on multiple different channels, in this case ports, that can exist between the same two people. And that's the same thing we see with TCP or UDP. So in this case, we have this conversation denoted by the Cincinnati ACK, and then we have some data. But if I scroll down a little bit, I see fins. Fins in TCP are used to actually signal the end of a conversation. So just like with TCP SYN, we have a fin flag set. Okay, see there's a fin flag set. And the fin has a four-way handshake. You do a fin, and then the other person acts it, and then the other person does a fin, and then act. So again, for sequence acknowledgement analysis, I just want to focus on one TCP stream between these two. So I'm going to write this one here below it is a little bit bigger. It's kind of, better example. So I'm going to right click on that SYN, right, for the next conversation. I'm going to right click, apply as a filter, or actually follow TCP stream. Now this is going to show you all the bytes here. It's all gibberish because like I said, it's encrypted. But let's go back, close it. You can see it now. The filter's changed to TCP stream 238. Still between the same source and destination, but this is just one of the specific conversations between those two addresses. Okay, so keep following me along. Now, the first few packets of data after the three-way handshake that are transmitted are what are known as TLS handshake packets. I'm not going to cover TLS handshake in this video. I have a whole other video on just troubleshooting TLS handshakes. But suffice to say, TLS is a protocol used on top of TCP to encrypt the TCP stream and also authenticate the TCP stream. So it's basically adding a layer of security. So I'm not actually going to be able to look into these packets to say what's in the packet in terms of data. Like I can't tell that this is a click or this is a grenade or whatever it is. But I can infer from what I'm seeing what's happening. So let's just suffice to say, after these packets, when you start seeing the application data packets show up, that's when the actual data between the client and server is being transmitted. So let's do a couple things here to get us ready for this analysis. Let's first just look at the pattern of data. So the way that TCP transmission works is that you send a segment of data or a chunk of data to the server, or the server sends a chunk of data to you, and then you need to acknowledge that data that you received it. We talked about this in the theory section, right? It's reliable because every piece of data is acknowledged. And the way that happens is that if I send a bunch of data, say these packets here, this packet, this packet, this packet, okay? This is from Shellshock to me. I need to now acknowledge that to the Shellshock server to say, hey, I got everything up to this point. You can send me more. Okay, so in this case, for example, I get these packets, and then what you'll see is an acknowledgement packet going back to Shellshock. Now this packet, just like we said before, it has an acknowledgement bit set. Okay, it's not part of a handshake, so it's not a three-way handshake packet, but it's the same thing. It's the same as this ACK, except it's not part of a handshake. Okay, and what happens is that this acknowledgement, this pattern will continue. Okay, so we acknowledge this. We're saying here that we've gotten all the data up to a certain point. Now, in order to actually see what that data is, we need to actually add some columns here to take a look at this. So I'm going to go in here. I'm going to find the sequence number and the acknowledgement number. Okay. Before we move to the next piece, you'll see two different types of numbers here: the sequence number, relative, and the raw sequence number. This is an important point, especially if you're getting into deep packet analysis. Wireshark will turn this number into this number to make it easier for you to interpret the data and to actually analyze the data. A relative sequence number always starts at 1 and then goes up from there, as opposed to the actual sequence number. This is the sequence number that's actually on that packet. If you capture this from another machine, you'll see this number. You won't see this number. And if I go back to the SYN, you can see here that it starts the sequence number at 0. And it starts the acknowledgement number at 0. So we've started you could choose either to analyze. If you're analyzing one capture by yourself, you can use the relative sequence number, and that's fine. It makes it a little bit easier to actually visualize and see what's going on. But just note, that's not the actual number on the packet itself. This is just Wireshark doing a calculation to make this number easier for you to see. So for the sake of an introduction to this analysis, I'm going to use the relative sequence number. So I'm going to right-click on this and apply it as a column. Okay. And I'm going to right-click on the acknowledgement number as applied as a column. Now, I haven't yet explained the acknowledgement number. I explained the sequence number a little bit, but let's explain the sequencing acknowledgement number now in a bit more detail. I want to change this length column. I'm going to show you why. The default length column in Wireshark is showing you the length of the frame. Okay. Meaning the frame is everything in that packet, including a whole bunch of stuff that is not related to TCP, meaning the frame, encapsulation, MAC addresses, IPs, things like that. To do sequence acknowledgement analysis, what you're looking for is the TCP segment length. This is specifically the data in the packet that is related to TCP. We'll talk about encapsulation in another video, but for now, what you want to do is actually get rid of this length field. And you want to actually add TCP segment length as a column. You can't see it on the window here. Let me just move this up. You apply as a column. And now you have sequence number, acknowledgement number, and you have TCP segment length. So let's explain what these two things are. Now, you know high level that TCP keeps track of the number of what data you've sent, right? It does that in two different ways. The sequence number, from the perspective of one host, so in this case, this is me, is the counter of how much and what data I've actually sent to you. Okay? You being the remote side, the server side. So I'm going to increment this starting at 0 for all the TCP data. That's why I wanted to have the TCP length here that I'm sending to you. And I mark that down on the packet so that when I send this packet, you know how many bytes of data you should have received. And let's see if that actually checks out. Okay. So sequence here, let's take a look here. The first two, or first one for me, I'm just going to look for it from my perspective, right? Sequence number 0. And segment length is 0. I'm not actually sending any TCP data in this SYN packet. It's just a SYN packet. There's no actual payload. Okay. The next packet I send is an acknowledgement. There's also no payload. Then I send a client hello message. Okay, this is part of the TLS handshake. The length of it is 2046. Okay. And what I'm expecting is the next packet I send to be marked with the current sequence, right? How much data I've sent so far, as well as how much I'm sending in this packet itself, which is 2046, and the total of that is 2047. So lo and behold, the next thing I send to the server is 2047. Okay, so I'm sending the data, but I'm also in this field indicating to the server, hey, I've sent you 247 bytes of data. Now, the next one I'm going to send, so I've sent until this packet, 2047. In this packet, I'm sending 80. So the next packet I send is going to be marked with a sequence number of 2127. Okay, so that is the how we keep track of the sequence number from my perspective. If I go in the opposite direction, it's the same thing. Okay, so in this case, 45 to 32. Okay, haven't sent any data, 0. Next one, no data. I'm going to keep it at 1, right? By convention, after the handshake, they set it to 1, so that's why we're starting at 1. The next packet I'm going to send, again, we start at 1. I'm at 1 at this point, but I'm going to add 256 to what's going to be the next number. If this packet is 256 bytes, and the previous was 1, it's 257. So in this case, 4532, it's 257. Okay. This packet, I don't send any data, it's 0. So the next packet is also going to be 257. Then I'm going to add 151 bytes of data in this packet, and now it's going to be up to 408. So in both directions, remember we have two different directions of data transfer. As I'm sending the packet, I'm incrementing the sequence number field with where I am in terms of how much data I previously sent, plus what I'm actually sending in this packet right now, so that the other side knows how much data they should have had, because that's important. Because imagine if you've only received like 10 bytes of data, and I'm telling you that I'm sending you 2127, or I've sent you 2,127 bytes of data, you're going to know there's a hole in the stream somewhere. Okay, and that's how one side will detect that there's actual packet loss. But in a nutshell, that's what the sequence number field is. So now let's talk about the acknowledgement number field. The acknowledgement number field is how you see what that receiver, okay, or sorry, what that whoever's sending this packet, how much data they've received from the other side. Now, again, this may be a little confusing, so if you need to go back and listen to this a couple times. But this is the acknowledgement number is how you keep track of how much the other side has sent you. Like you're basically saying, this is what I got so far. So sequence number, this is what I've sent. I'm telling you, hey, 45, I've sent this much. Acknowledgement number is me saying, this is how much I've received. And you can see already, this is how we keep track of TCP sequences and how much data has been sent. I'm going to tell you every time how much data I've sent and how much I've received. And you're going to do the same thing back to me. And we're going to be able to tell if those things go out of sequence, right? Again, this is why we have to synchronize the sequence number. So let's follow some of these examples, right? So we have, here we have 10s or 10, this is me, okay? I'm at sequence number 2047. So this is what I've sent up to. I've told the other side that I've received from them 250, or I've received 256 bytes, and I'm waiting for 257. So the acknowledgement number actually goes up by 1, because what it's telling the other side is, I've received everything up to the one under this, 256, and what I'm anticipating next for you to send is 257. Okay, so let's just try to follow the pattern here, and we'll go through a few of these so we can actually get the pattern down. So let's see, 257 is what I'm expecting. This is my server. Okay. Now the next thing that comes in from the other side, from Shell Shock, their sequence number is 257. Right? And let's change the order. So that 257 is what they're expecting, or what I was expecting, and then lo and behold, the other side sent 257. Now the other side, this one has no data. It sends another packet that has 151 bytes of data, okay? But what my acknowledgement field is saying is, hey, I've got everything up to 3186 bytes of data. And what I'm expecting next is 3187. Like the sequence number you're going to be sending me is 3187. And over here you can see, lo and behold, it's 3187 coming back from me. And we'll flip the order again. I send a bit of data over, okay? But I'm now I'm going to say, well, I sent you some data from your side. I have everything up to 432 bytes. Now, sequence number 432. I would like to actually get the next thing I'm anticipating is 433 in terms of your sequence number, and then that's what I get is 433. And the pattern continues, right? So if I send some data, but then now I'm saying to you, well, I anticipate that your next packet is, I've received everything up to 3407. I'm anticipating your next packet is 3408, and then here's 3408. So that is how the TCP send and receiver keep synchronized with one another to understand what data has been sent, how much I've sent, and then how much I've received from you. And these numbers just keep going. So as an exercise, I would definitely try doing any sort of TCP capture and try to follow through the sequence and acknowledgement number analysis like this. Start with relative numbers because it's much easier to calculate in your head. But when you get better at this, you can actually do it using the raw sequence numbers because that's actually more close to real than these are, because that allows you to do like cross-platform analysis and things like that. All right, so let's put this all together. So we have, in essence here, data being transferred from one side. So let's say this is from the Shellshock IO server, right? We have 51 bytes, 51 bytes, 51 bytes. What comes back from the other side is a packet where the acknowledgement flag is set. So if I go to flags, acknowledgement is set. And the acknowledgement number is set, right? We said, remember, there's a relative and there's a raw. The relative number is 3368. So what this is doing, okay, the acknowledgement number, we know how to keep track of them, we know how to calculate them, is signaling back to the sender, this is what I have. Okay, you sent all this stuff, I'm going to send an acknowledgement. The acknowledgement is to tell you, hey, I've got up until this. And then the same thing goes back the other way, okay? Now, in some cases, you send data to the other side, and then the other side sends data back to you, and you go back and forth that way. In some cases, it's one way. It's just one-way data transfer. So in this case, for example, we have 51, 51, 51. 0 bytes, this is what's known as a naked acknowledgement, meaning we are just sending a TCP packet back to Shellshock to say, hey, I got everything up to 3368, but I don't have anything to send back to you at this time. And you'll notice that when you're actually looking at the Shellshock traffic pattern, you'll see here, we see like the server sending me 51, 51, 0, 51, 51, 0, 38, 27, 0. This is kind of what we had mentioned before, right? Which is we anticipate that most of the data transfer is going to be from the web server to us, and then occasionally we're going to send data back to them. So let's find an example of us sending data back to them. So I'm going to look for a source of 10.0.10.43 with a non-zero packet length. So I might have to take a bit of time. And here we go. So you can see here, here's a packet going back to Shellshock, right, to 45. There's actually some data in it. Now, the acknowledgement packet doesn't necessarily have to come right away, okay? But the acknowledgement packet can come later on, right? It could come like right, subsequently after, but it has to come shortly after in the stream. It can't come like way too late. Otherwise, the whole thing will stop. Okay, so let's try to pick out where this acknowledgement packet is. So in this case, I send this data to Shellshock. My sequence is 3498. My acknowledgement number is this. Okay, and my data is this. So now I'm looking for an acknowledgement number from the Shellshock server that says, I got this packet and I got this data in it too. So 3498 plus 29, that's going to be like 3527. And then we look for that packet. Boom. The acknowledgement number coming back from Shellshock is 3527. Meaning, at this packet here, remember I said you could jump a few packets because other things may be in flight. I'm acknowledging that I got this packet here. Okay, because I said this is what I have. I added this. I want to make sure the other side has everything, and this is the other side saying yes, I've got it. So this is in effect how TCP works, but also how to actually do the analysis of sequence and acknowledgement so that you can understand and track how the conversation is going. In a future video, I'll talk about things like the retransmission mechanism, how to detect holes, what duplicate acts are, what retransmissions are, how different algorithms work with TCP to kind of recover from loss. But for now, I'd recommend doing a capture of some TCP data, right? It doesn't have to be Shellshockers or a game. It could be something else. Add your sequence number, acknowledgement number columns, and then run through it to see if you can actually follow through a pattern of sequence and acknowledgement numbers to track how the data is being transferred and how the numbers are keeping up. And without further ado, just to end off, let's play some more Shellshock with TCP lag. Oh, that guy almost got me. Kind of stuck in no man's land here. Oh, 2 of them are after me. Oh, look at that. Oh, look. I can't move. Got him. These guys don't know I'm here. These guys don't know I'm here. Wow, you guys suck. All right, that's enough. That's it for this video. If you enjoyed it, please like and subscribe. And if you have any questions on the topic we've covered, please join the Discord server where we talk all things network. Until next time.